Hi, my name's Andy Spoon. In this video we're going to take a look at an LRC setup with PASCO Capstone and the 850 Universal Interface. Let's begin by taking a look at our LRC circuit setup. I'm going to be using the UI5210 circuit board. On the circuit board I'm going to be using the first inductor component, the first capacitor component, and the second resistor component. Connected to my 850 interface, in channel A I have a voltage sensor measuring the voltage across the entire circuit. In channel B, I have a voltage sensor measuring the voltage across my second resistor, and my signal generator is attached across the entire circuit. Now let's take a look at PASCO Capstone and getting set up inside of our software. I'm going to begin by going to my hardware setup and adding my two voltage sensors. I can do that by clicking on the channel, typing the first few letters of the sensor, and then confirming it with the enter button. So I'm going to add my two voltage sensors. I'm now ready to go set up my signal generator. So I'm going to click on my signal generator and I'll be using output 1. I'm going to create a single sweep sine wave that's going to be looking at a range of frequencies across the circuit, hoping to find the resonating frequency for the LRC setup somewhere approximately in the middle of my time range. So let's go ahead and turn on the single sweep. We're going to be using an amplitude of 3 volts. We're going to start our initial frequency at 1000 Hertz. Our final frequency is going to be at 70,000 Hertz over a duration of 25 seconds in steps of 1 Hertz. Once your signal generator is set up, we can now go ahead and pin that to our screen and open up a full screen scope beside it. So let's go ahead and get our scope set up. I'm going to begin by adding channel A to my left axis. I'm going to insert a second y-axis and add my channel B voltage sensor. I'm going to go ahead and turn on my trigger. This will trigger on voltage from channel A. I'm also going to go ahead and adjust my axis. So I know that my amplitude max is 3 volts. So I'm going to go ahead and adjust both of my y-axis ranges so that they max out near 3 volts. I'm also going to go ahead and adjust my time axis. Now notice whenever I start adjusting my time axis, my sample rate is automatically changing along with it. And what Capstone is trying to do is adjust the sample rate so you're getting the maximum number of points to fill up your oscilloscope display. Now for this particular setup, I'm going to be using components that are resonating approximately around 30,000 to 35,000 Hertz. So I'm going to want to get a sample rate of approximately 5 megahertz. So as you can see, approximately there, I'm at a scale of 0 to 0.00008 seconds. So that's approximately the scale I'm going to be using. The last thing I want to do is change my record mode from continuous to fast monitor. And this will change the record button to a monitor button. I'm now ready to begin monitoring my voltages. So I'm going to press the monitor button and I'm going to turn my signal generator on. You'll notice I instantly have 2 different waves that come into view in my oscilloscope. They begin out of phase with each other. As I approach the resonating frequency, they go into phase. As they go beyond the resonating frequency, they go out of phase with each other, and my amplitudes begin to decrease. And we'll just wait a second and watch the signal generator run through the entire 25 seconds. Afterwards, there's no signal produced, so you shouldn't see anything in your oscilloscope. So let's go ahead and turn off our signal generator, stop our monitoring. I'm going to run through that one more time, and this time I'm going to try to stop it approximately on where the resonating frequency is. So let's begin monitoring and turn it on. And right as the waves come right in phase with each other, I'm going to try to stop it. And by clicking on the stop monitor button, that will freeze the data in my oscilloscope display. So let's go ahead and stop our signal generator also. Now, ideally I would be able to also get the information about what frequencies I'm looking at that's causing that resonation. So I'm going to use my FFT display to identify exactly what frequency that is. So let's open up a second FFT window. I'm going to add voltage from channel A to that. The first thing I want to do is go ahead and tell it to manually adjust the frequency range, and this will disconnect the link between the sampling rate and the frequency range of my FFT display. By doing that, I can now manually zoom in on my frequency axis, and I want to get that so that it covers the full range of my signal generator, so 0 to approximately 100,000 hertz should do it. I'm also going to go ahead and zoom in on my y-axis, once again knowing that 3 volts is going to be my maximum amplitude. Now, as you can see, my bin size right now is fairly large, and it's covering a lot of frequency range, so that's going to be hard for me to identify exactly what frequency the resonation is happening at. So I'm going to go into my FFT properties and change my bin size. So maximum number of bins is currently 2,048. I'm going to increase that to 8,192 and confirm that by pressing OK. I'm now able to go ahead and manually increase the number of bins that it's using by using the increase and decrease number of bin buttons in the FFT toolbar. Notice we can also scale the FFT display to fit. Okay, now as you can see, I'm starting to have some clear symbols exactly where my resonating frequency is. And to confirm what that bin is, I'm going to use my Smart tool. And notice the Smart tool will try to automatically snap to the closest data point. So let it go, let it snap to the data point. All right, so there it tells me that my frequency that I'm currently looking at from channel A is 30,500 hertz. And if I want to see a couple of extra decimal points there, I can also right-click on the tool, open up its tool properties, and increase its number of significant figures. And I can see that it's actually 30,518 hertz. That's pretty close to what I'm expecting for this setup. Obviously, I can try to go through it again. I can adjust my bin sizes if we want to try to use that to get a clear idea of exactly where that resonating frequency is. Notice as I increase my number of bins, I've now got it to 32,300 hertz, and that's very close to what I expect the theoretical resonating frequency to be for this setup. Thanks for joining us in this video. I hope you learned how to set up an LRC circuit for your classroom.